Okay, so for this homework problem, we have some bar with a constant thermal diffusivity, which is alpha, just meaning that heat is going to transfer the same all throughout this bar. We have these lengths between these equally spaced notches, which have some delta x, and each section is going to have some temperature, so some Ti. And we also know that based on what our Ti is, we'll also have some Ti plus 1 and some Ti minus 1 like this, and that's how we can refer to each different section. We'll say that delta x is constant throughout, so evenly spaced sections, and then we'll have some cross-sectional area, which is also constant throughout. And sorry for the bad drawing. So if we were going to go ahead and solve this problem, how would we start? Well, we'd probably want to start with an energy balance. So we'll say that the temperature changes as time changes. Okay, great. And that's going to give us some temperature over time terms, so some kelvins per second or Celsius per hour or something like that. But we want to try and go ahead and get to joules per second. That is going to be our desired unit. So how do we do that? Well, the first thing we probably want to do is multiply the volume to try and get some new terms in there. So our volume is going to be just whatever our cross-sectional area is times delta x. So we can say that we have A, delta x, and then our differential equation. Does that get us to joules per second? Well, not quite. We're still missing one term, which we're going to need, which is our density term. So I think our final equation here is going to be rho A delta x dt over, or dti over dt. So this is going to be our final equation that sets us up to have units of joules per second and our balance that we can go ahead and move forward with. And then sorry, we also need to multiply by C, that and that will get us into normalized units. So multiply by that C, rho A delta x over times how our temperature changes with time. Okay, moving on. We have Fourier's law, which is something we learned in heat transfer. This is a core equation in chemical engineering, and Fourier's law is Q is equal to minus Ka dt over dx. So if we go ahead and look back at our bar, if we imagine that our heat is propagating from right to left, from our middle, from this point in our middle to the next point in our middle to our right, we know that that is going to be equal to some dt dx as our temperature changes as we go the other way, or as we change direction. But also we know that we can propagate negatively. We can go to the left. So we want to write our equation such that CPA delta x, sorry about that, CPA delta x, and then our differential is going to be equal to, well, minus Ka is going to be constant. That's always going to be the same thing. Since our area is constant, we'll have some heat transfer coefficient. But then we can say we have some T1 minus T naught over our delta x. That's that dt over dx. We also need to subtract, because we're going to be propagating some in the other direction as well. So we can also subtract T naught minus T1, right? Because we'll be propagating that other way, delta x. So this is what our equation should look like. Great. Now we can move on to using our thermal diffusivity term. Okay, great. Moving on, we know that alpha, our thermal diffusivity, is equal to K over rho times C. And knowing that, we can really go ahead and do some algebra and simplify this equation a little bit. So the first thing that I'm going to do is cancel out these cross-sectional areas since they're on both sides. Then we're going to go ahead and divide by K. So we'll have Cp over K on the left. The inverse And that looks a lot like the alpha, just the inverse, so we can just have the inverse of alpha. So plugging in, we can write that Cp over minus k delta x dti over dt, like this. Oh, sorry, let me turn my brightness. Oh, my brightness is max. Got a little bit of a glare, sorry. Let me actually get rid of that glare. Okay, perfect, the glare is gone. I guess it's not, whoops. So we have this, and then that is the inverse of alpha. So then we can say that we have delta x over alpha times dt I over delta t, like that. And we can say that this is still equal to our, and then over here on the right, we have delta x as a common denominator, so we can go ahead and add these terms. So we can say that we have ti plus 1 minus t, or sorry, plus ti minus 1 minus 2 ti all over delta x. Okay, perfect. But we're not quite done just yet. So we have this is our equation. We're not done. We can multiply delta x on both sides. So we can say, and we can also break this term out in pink here. So what can we say that is? Well, we can say that the differential of ti and t, we can say that this pink term is going to be equal to ti raised to some n plus 1, where we can choose n. We can add that to some ti of n, and that's going to be over some delta t. So now we have this algebraically, and perfect, we can go ahead and plug that in. So then we have delta x over alpha, and we multiply both sides by delta x, so delta x squared times, we have this ti n plus 1 plus ti n all over delta t, and that is equal to ti plus 1 plus ti minus 1 minus 2 ti, like this. Perfect. And now we just need to go ahead and group some of these terms. Okay, so now we have everything set up. We just need to do a little bit more algebra. So remember, we're looking for this term here. This is going to tell us how our temperature changes as we propagate through that bar. So let's just go ahead and solve for that. So doing some algebra, we have ti n plus 1 minus ti n is going to be equal to alpha delta t over delta x squared. That's going to be equal to this whole long term here. I can write that down for just now. Then adding tin, we can say that ti n plus 1 equal to ti n plus alpha delta t over delta x squared times this t, this long term ti plus 1 to the n plus t to the n I minus 1 minus 2 t n 2 ti.
As it navigates through time. So now let's use Python to kind of model our situation here and kind of develop this temperature profile as it goes through time. So coming back here, I kind of want to condense maybe this little term here into just one term that I can kind of change according to how I want it to. So I'm going to call this R, and we will also code that into Python. So let's just start doing that. So our initial state here is that our Our bar is at a uniform 20 degrees Celsius. And
Okay, so if we move over to Python, the first thing we're going to do is call. Oops, sorry, those are my messages. First thing we're going to do is define this term, and we're going to call it R. So we have some alpha. I guess we can just go ahead and call that 1 for now. We have some dx. We can go ahead and call that 0.5, I guess. And then we have some dt, our time interval, and I guess we can call that 0.1. And we can define R, and we can say that that is equal to alpha times dt, and that is all divided by dx squared. Shift enter. Okay, well, my bad. Shift enter. Is that not how you do it? Okay, so now we can go and check R. Okay, so we're good there. Moving on. Okay, awesome. So now we need to add something about how many points in our array we'll have. For now, we'll just call that 100. We know R. We can say that our array is going to be, call our array T for our different temperature and for our gradients. So I'm going to say it's equal to np dot full. We need to go from 0 to 50, I think, like this. Shift enter. T. No, that's not what we want. We need to fix that a little bit. So I think we need to do it like this. We need to go from n, and I think we only need 20 points. So now if we see what our t is, okay, yeah, that looks good. So now what else do we need to say? Oh, I guess that's fine. We can do it on a different line. Delete that. Okay, we want to say that we're going from, we want to say our n0, our initial value, I guess we can call that 50, and then, well, actually we don't want n, it's just our number. We want our t, and then we want our t at our end. I don't know, I guess we can call that equal to 80 or something. T, shift enter. Okay, perfect. So our array looks good so far. Let's go ahead and move on. Okay, so this looks all fine and dandy, but how are we going to propagate these numbers in the middle? Well, if we look at, say we want to go from our beginning to our end, so from t1 to t minus 1, and we shift enter that, well, we can see that all the numbers are the exact same. That's not what we want. We want to keep these end values, but we also want to propagate in the middle. So instead, we're going to go from our t from 1 to minus 1, and that needs to equal, well, it needs to equal what we had derived earlier. So we want to say that it's going to be equal to our r, which is going to cause our propagation, going to cause those temperatures to change, times our t from, we're just going to go I plus 1, so that's just going to be like this, plus t I minus 1, so I believe that's going to be from 1 to, from 0 to minus 2, and then minus 2 times t from 1 to minus 1, like this. Okay, shift enter. Something didn't quite work out there. Do it like this maybe. Could not. Bracket. Okay, let's check this out. Okay, a few small errors. This just needs to go to minus 2. Since we have that I minus 1 value, this just needs to go like this. And we also need to remember that we are adding to our thing here. So we need to start with our initial t to 1 to minus 1 plus, and if we do it like this and we shift enter, it should run. So now that we can see that t from 1 to minus 1. Okay, and we can see that those n values are starting to change. But if we just run our t, we can see that, okay, our values in the middle are starting to change. We're still beginning at 50, ending at 80, but these endpoints are starting to creep in. So we can go ahead and make that run across the entire gradient. Okay, so how do we make this go through the whole thing? Well, we need to create a new variable probably, so we can call that our t profile, and let's go ahead and make a copy of that. So we can say that that's equal to t we say that is equal to some t copy, okay, like this, and then we need to create a loop, so we can say for I in for an I in range however many points we want. Since we used n equals 100 earlier, we'll just say our range is 100. Go ahead and tab this. And then we need to make sure that our value is constantly changing to get these middle values like they should be. And so to do that, we need to append. So we just need to say our t profile append needs to be equal to our t underscore copy, that value that we're storing, like this. We shift enter. Okay, that's not going to run because t copy is not defined because it's not a value. So I think we just kind of instead need to write it like this. Append it like that. Okay, it's still saying t prof is not defined. Okay, we need to shift enter, run that. T copy is not defined, and that's because t underscore copy is a name. We want to dot copy to copy it, so we should be able to shift enter that. Perfect. And now if we add a period there, saying that this is not available, maybe throw some parentheses around it, like that. Okay, perfect. So now, when we go from 1 to minus 1 throughout our entire range, we're getting some different values, but that's not really what we're looking for. So what we actually want to look for is our t profile. We want to look for our t profile at -1, and when we do that, okay, so everything looks good. Let's go ahead and code this up, make our chart. Let's go ahead and fig underscore make dot subplots. We'll fix that in a second. So 4k in something like this, maybe. We want to fig dot add underscore scatter. We want our x to be equal to, okay, I really wish that would go away. X is going to be, we want to arrange our x with our k values like this. And, no, I'm sorry, x needs to be our x dot arrange, like this maybe. And y just needs to equal k. And then we need to it equals show, like this. Okay, why didn't it run? Quite a few things we did wrong. First things first is we just want to fig.show. We need to numpy arrange, so it's an actual function. We want to arrange in terms of our n, which is our number of iterations, like this, and then with our y, so equaling k. So I'm not sure why that just showed. Oh, because it might be because this is still in the function. Fig.show. I don't know why that is happening. I think maybe if we just add, okay, here we go. Yeah, and there we go. We can see our temperature propagation as our time goes along here. Looks very nice. Moving on. Okay, I don't exactly remember where I left off, but I think I had my plot and it hadn't converged yet. It just kind of was like a dip. We didn't have this convergence. I don't know why I could not get my array to be right, but we figured it out. So here's our array of our temperature profile. Here's all the code, same code as I had before. We made our plot, and here it is. We can see more points, or we can see less points. This will be more points. Yeah, we can see how eventually it just propagates right into our profile. We can see, try to show a few more points, or a few less points. Here we can see again how we're going to converge here. So yeah, there's our graph. I ended up having to up the iterations for it to converge, so I don't know why that was a thing, but it's working well now. So what we want to do is change our R values. So let's go ahead and get a few more points on here. Maybe something like this. Okay, yeah, that looks good. So we want to try and see our R value if it's, say, above 0.5. Right, right now we've established R is 0.4. But if we make it, sorry about that. If we make R equal to something slightly above a half, so 0.503 maybe. I don't know why that happened. Maybe we need some more points to propagate. So now it's just going back to not converging. Okay, now we're going back to the same issue we had before. I really hope this doesn't screw me. Oh my gosh. You saw the data that was right before. Let me fix this. So I think anything under 10,000 iterations we're just not converging for some reason. So I'm going to keep this I at 10,000. And yeah, it should be fine. We see we have that. We'll see we have this nice graph. But if we make R something not as good, we make R something slightly above a half. So we make R equal to 0.503. Keep those same iterations. Look at that funky data. And now we get this graph that just doesn't really help us with anything at all. So this weird wave-like behavior shows why it's really important to pick these values correctly. Your distance and your time and your alpha value. So like for instance, if we go just a slight change, if we go 0.499, you can see we're still getting some pretty typical behavior as we were getting before. So it just shows it's so crucial to pick these values correctly. But we can actually explain why we get this funky curve when we get that R over a half using something called the von Neumann equations, I believe. So let's go ahead and switch back to the iPad and show that. Okay, we're back on the iPad here. And we have this equation, which we showed before, and it can have some solution here. And what we need to do is take two derivatives of the given equation here so that we can get to what we want to prove. So we can say, here's our solution. We need to take the first derivative of that solution. So we can say that first derivative d partial temperature with respect to time is going to be equal to minus alpha times k, and then that's going to be times e to the minus alpha kt, e to the I kx. Like this. Okay, there's our first derivative. Okay, this looks good. We can also rewrite this as minus alpha k squared t, because we said that our solution t is these two e values multiplied together. So now we need to go ahead and take the derivative of our temperature with respect to x, the first derivative of that, which is going to be I squared kx, I believe. No, I'm sorry. It's just going to be I kx here. But then when we take our second derivative, this should look like original equation. So partial second derivative like this. Then we get that our I squared k squared x, we know that I is equal to the square root of minus 1. So when you square that, it's just minus 1. We'll cancel out that negative sign. I'm sorry, there's no negative sign here. So we can just say that that second derivative is equal to k squared x. I'm sorry, minus k squared x. I'm sorry, I had x's previously, there should have been t's. So we have this. And then if we go ahead and if we go ahead and plug that back in, up here we can see that we get minus alpha k squared t is going to be equal to what we just derived, minus alpha k squared t. Like this. Okay, perfect. So we have proved that those two things are equal. So this is good. By proving that these two things are equal, we have satisfied that this is indeed a solution for our problem. Let's get a little bit more suspicious in depth. Let's add some tjn to this so we can add a position. So we can say that this is going to be equal to e to the minus will work, minus alpha k squared, and then instead of t, we're going to replace that with some position n and delta t to see how our t changes. And we also have e to the I k, and then some j times delta x as our position changes. So now we have this nice equation for what we already derived, but with a position. Okay, moving on. Remember, this tjn is just for our middle term. We can propagate left and we can propagate right, so we can say that tj minus 1 to the n is equal to e minus alpha k squared n delta t times e I k j minus 1 delta x. We can distribute, and we can say that this term is actually equal to e I k delta x j minus that I k delta x, like this. But then we can actually see that, sorry, this should just say t. We can actually see that this term, these two terms are actually just our t, and that's all that is left over. So we can actually just rewrite this at tj minus 1n is going to be equal to our t times our e to the minus I k delta x. And we can do the same thing for j plus 1. We can say that tj plus 1 is equal to te I k delta x, like this. Perfect. So moving on. So now what we can actually do is go back to this equation before, where we had our tj n plus 1, we had our R term, and we can just pull out this TIN from everywhere. And when we do that, we can say that TJN it's going to be equal to 1 plus R times, and then we can pull out all of these terms. So our first term is Ti plus 1N. So we already solved for that, so we already pulled out that, or sorry, it's J. So we can say that that's, all that's left is EIK delta X minus 2, because we just have 2 of our TJN, and then plus our E to the minus IK delta X, and that is all going to equal TJN plus 1, like this. Okay, fantastic. Okay, and we can also, so here's our equation. Look at, oh, I'm sorry about that music. So we have Euler's identity here, where we have e to the I kx is equal to cos kx, k delta x plus I sine k delta x. Good old throwback to calculus. So what we can do is actually plug this in, and we can see that Tj plus 1 is equal to Tjn 1 plus R. So we can see that we're adding these two terms together inside the parentheses, so these sine terms will cancel and we'll just have cosine terms. So 1 plus R, 2 cosine k delta x minus 2. Okay, there we go. We know that for this Tjn plus 1 term, anything less than -1 or greater than 1 is going to cause it to go to infinity, and our graph is going to be no good. So we can actually set up an inequality where we know that we need that term to be or greater than -1 or less than or equal to 1. So we can say that 1 is, oh, sorry, new page, less than or equal to Tjn 1 plus R 2 cos k delta x minus 2, and that term has to be less than or equal to +1. Oh, got my eraser out, sorry. So here's our inequality, and we know that cosine has two extremes. So when cosine is 0, or when our argument is 0, cosine is going to be equal to 1. That would be all the way on the right. And when cosine is equal to, or the argument is equal to pi, cosine is going to be -1. So hypothetically, let's just say for right now that k delta x is equal to, we'll just call it pi. So that term is going to turn into -1. Call it equals pi. So the first thing we want to do is we'll say -1 is equal to, and again this TGN term can disappear because that's just some multiplier. So we can say that we have 1 plus R times 2 times -1, because when cosine is pi, we're at minus, the value is -1, minus 2 less than or equal to 1. Okay, so now we just have to solve this algebraically. We can subtract from 1 on both sides, so -2 less than or equal to R times -4 less than or equal to 0. And when we divide by -4, we can say that 1/2 has to be less than or equal to R. But we actually need to flip the sign because we're dividing by a negative number. We could all throw back to algebra. So we can actually say that 1/2 has to be greater than or equal to R. We just solved that algebraically. And we know that we saw that before. We can plug in 0.5 for R. We can plug in 0.499 for R, and we're okay. But the second we go over that 0.5, it's no good. And so we can do the same if we say that cosine is equal to 0, we can say that that's equal to 1. So we can say that minus 1 plus r, 2 times, instead of minus 1 this time, it's going to be 1, minus 2, equal to 1. Okay, so we're going to get that minus 2 is equal to, it's just going to end up being 0. So that term doesn't really matter because the inside of it will be 0. But we proved here algebraically that r term is always going to be going to need to be less than a half, or else this is just going to go to infinity and give us these weird cosine curves that we can't do anything with. So thank you for watching. Please let me know if there are any questions. We'll see you in part 2.